Building complex applications with large language models forces developers into an immediate mathematical trap. You need elite reasoning for logic-heavy architecture, but those same frontier models rapidly burn through strict API rate limits. This illustrates the trade-off. Routing an application loop through Opus fills its massive context window instantly, hitting a rate limit penalty. Alternatively, routing through Sonnet works for standard implementation, but halts completely at complex decisions requiring deep logic. Most standard agent frameworks ignore this reality. They are structured to get code out the door quickly, rather than orchestrating how many tokens it takes to get there. You are left paying premium compute costs on simple syntax errors, or accepting lower code quality just to keep your session alive. Running Opus as a solo agent drains your budget, and running Sonnet solo caps your capability. To scale an application efficiently, the routing mechanism itself has to change. Anthropic engineered a specific solution to bypass this exact bottleneck. They call it the advisor strategy. The strategy decouples routine execution from deep reasoning. It forces models into a strict two-agent hierarchy where the workhorse operates constantly, and the frontier model acts strictly as a quiet overseer. We are going to construct this exact architecture to measure exactly how much compute it saves. We will also test it against real-world code bases to expose the structural breaking points where this multi-agent logic loop fails entirely. Building this system starts at the ground floor with the primary agent, the executive. Look at this architecture map. The executive runs exclusively on Sonnet. It handles the continuous main loop, writing routine implementation, executing tool calls, and generating user outputs. Sitting isolated above it is the secondary agent, the advisor, running on Opus 4.6. The architectural rule here is strict. The advisor never writes code or makes direct system changes. During routine tasks, the connection between the two remains completely inactive. The link only opens when the executive hits a logic failure state and explicitly requests guidance. By locking Opus out of the continuous feedback loop, you eliminate the massive overhead of sending its full context window back and forth for minor syntax tweaks. Invoking Opus strictly for targeted performance gaps drastically drops your overall token consumption. A standard 5-hour API limit suddenly stretches far further, allowing you to sustain long development sessions. To test this, we deployed the hierarchy on an application suffering from a real-time state syncing error. Deletions made on one device were failing to reflect across other sessions. Operating as a solo agent, Sonnet attempted multiple independent fixes. It repeatedly failed to resolve the underlying deletion logic. Instead of hallucinating a new, incorrect fix, Sonnet halted the loop and cast the entire conversation history upward to the advisor. Opus analyzed the state sync breaking point and formulated a precise structural solution, returning it as a plain-text payload. The executive absorbed the advice and independently executed the specific code adjustments across the repository. Upon testing, the cross-device dilution sync performed perfectly. When a smaller model gets stuck on its own, it enters a cycle of endless failed prompts. This hierarchy intercepted that failure early, saving the context window from being drained by useless trial and error. Next, we pushed a major structural overhaul, instructing the system to entirely replace a core UI library. Sonnet began by utilizing a playwright integration to map the current layout and state of the client-side UI. Recognizing the high probability of breaking the application, Sonnet halted. It proactively queried the advisor before initiating a single code change. Opus caught a critical flaw immediately. It identified that the existing project dependencies and the requested new library had severe version conflicts. Guided by that warning, Sonnet updated the dependencies first, secured a stable environment, and then systematically redesigned each component. The multi-agent setup acts as a structural failsafe. It forces a rigorous reasoning check before mass code execution starts, preventing application-wide crashes. While the UI migration succeeded, it exposed a massive hidden cost embedded in the workflow. As shown here on the bottom timeline, the entire operation took 31 minutes to complete. The delay lies in the model capabilities. Smaller models like Sonnet lack the orchestration depth to spin up multiple parallel sub-agents to handle a massive workload. A frontier model like Opus instinctively optimizes.
It identifies independent tasks and processes them simultaneously, collapsing the overall timeline. By delegating the execution layer entirely to Sonnet, you are forcing complex overhauls through a single file line. For massive codebase refactors, the raw time you waste waiting for a sequential bottleneck completely negates any compute budget you saved on tokens. The system has another structural flaw. The primary agent can easily misjudge the scope of the problem it is trying to solve. We ordered the agent to build a brand new real-time streaming feature into an existing application. Viewing it as straightforward implementation, Sonnet completely bypassed the advisor node. Without that reasoning layer to check its logic, it chose the wrong component architecture. The styling meant for a single preview pane leaked out and corrupted the entire distributed state of the application. To recover from this, we had to intervene manually, explicitly prompting the agent to invoke the advisor and identify the architectural error it had just created. This framework excels under specific conditions. It is built for simple to medium-scale applications, where the work is mostly straightforward implementation, requiring only occasional deep reasoning. But if you are building an application with massive computational complexity, dense dependencies, and multiple cascading failure points, bypassing the hierarchy is safer. In those environments, running Opus directly as your primary agent is the definitive, most cost-effective use of your time.